Well, welcome, or I hope for most of you, welcome back to this installment of the Delegate Lecture Series. We're very pleased to have Jon Kleinberg from Cornell University, and as you see, the title is Probabilistic Models for Cascading Processes in Networks. And you better be better behaved than the 17-year-olds you talked to this morning.
That was a lot of fun. Yeah, so I'm back from Ward Melville High School, and so thanks for coming. So what I want to talk about today was actually some of the mathematical and particular kind of graph theoretic and discrete probabilistic ideas behind some of the issues that I talked about last night in the lecture related to cascading behavior and threshold models of contagion. And so the focus here is going to be on, actually, sort of in short order, I'll try to zero in on an extremely simply stated problem about a form of contagion on networks, which was motivated by some of what I'll talk about here. And it turned out it was really very hard to find any techniques that let us analyze this, right? So it's going to be a very simple toy model, so it's not going to be trying to exactly capture the dynamics of any real thing in particular. But it seems to be a sort of common, simple model that's sort of a special case of many of the other things that we had thought about. And so we tried to dig into that. It led to a number of graph theoretic issues that we sort of had to wrestle with. And so that's going to be the focus of the talk, how to think about local neighborhoods of graphs and how they respond to contagion in this very, very simple model. OK, that's just by way of context. So it'll focus on that model. It's joint work with sort of a collaboration between some theoretical computer scientists, Bobby Kleinberg and Ava Tardosh, my colleagues in CS, and then we worked with Larry Bloom and David Easley, who are microeconomic theorists in the economics department. David sort of has this dual life as a financial markets person and a microeconomic theorist, and so he sort of does empirical work on financial markets and then also some theory. And in some sense, part of what we're going to talk about comes out of some of the intuitions he sort of conveyed to us about what he sort of was hoping to find in a model for cascading failures in that context. So there are obviously people in the audience who know infinitely more about financial markets than I do, but I'll channel some of the intuition that David had in sort of laying out this problem. OK, so I think that's all the context. So contagion networks, just to kind of hark back to the themes from my talk last night. And my talk last night had a bunch of these pictures, but this is just sort of the segue into the current talk, which will have much more stylized pictures, not these. But contagion can both be a good thing. It can be sort of spread awareness of new products. It can spread awareness of new social movements, new online groups. It can also be a bad thing. And I'm going to sort of take the kind of bad interpretation for much of what I'm talking about. Contagion can also be something destructive that spreads through networks. And sort of we think about disease. We think about financial contagion. All of these are things that can spread destructively through networks. And so in the end, the mathematical question will be the same. What is the probability this node gets hit by the contagion? But my sort of connotation will be sort of that we're trying to minimize that probability. OK, good. So what are some reasonable models of this? So we thought about existing models of financial contagion. And they're actually, I'm not going to attempt to survey that really, because I'm going to try to zero in on a very simple model. But one thing that was sort of at the heart of all these was the following distinction. So if you think about how one standardly models disease epidemics, there's this thing called the SIR model, susceptible, infectious, removed. And at the heart of it is sort of this idea of independent contagion. Namely, here's V. We're trying to decide if V is going to be affected by this disease spreading through the network. And here are nodes 1, 2, 3, 4, and they become maybe infected sequentially. And each of them has this chance to infect V. A coin gets flipped with probability P, and they either infect V or not. Right? So if I look at V over the course of successive exposures, it's like it's getting exposed to repeated coin flips. And if it gets infected, it then has a chance to infect some neighbors downstream here. Starting in the bunch of work in the 70s, and this was sort of implicit in one of my slides from last night, there was this idea of what I'll call threshold contagion. I'll call it threshold contagion for a reason that'll become more apparent on the next slide. Right now, let's just call it non-uniform contagion, which is that the jth exposure to an affected node carries a probability pj of becoming affected. Right? So all links here are equal, but what matters is that the second time you get hit with a thing, there's a different chance of being infected than the first time, and so forth. And different domains have actually proposed different versions of this. So in social contagion, and we saw this corroborated by a bunch of the plots from last night with data from Facebook and other places, that often the first few shocks have the greatest impact, right? So if you're looking at, joining of an online group, having one friend or having two friends seems to sort of have the single biggest effect, and then the third and the fourth is sort of this attenuating influence. And as I mentioned in the talk last night, causality here is very complicated, but at least from, if we were going to build a generative model. So here's where I begin channeling one of the pieces of intuition that David Easley came to us with, which is that somehow the financial contagion story, if you sort of go to the heart of those models, it's inverted. That essentially anything where, say, the first, so these are now your neighbors in some financial network, this person has failed, and maybe you had some, there was some debt they were going to repay you, and now they can't because they failed. That now hurts you. It diminishes your inventory, which makes you weaker when you get hit by the second shock from someone else who can't repay you. And so, in fact, the probability of failure is now going up, right? Because each shock hits you after you've already been weakened, right? Which is very different from this, where social contagion, each shock hits you after you've already seen the idea, you rejected it, so the chance you're going to accept it now is different, right? So it's a totally different interpretation. And so this is actually where things get difficult, right? So there's a lot more known about how to handle this kind of stuff, but this one turned out to get very, very messy. OK, so first of all, this idea of successive shocks is sort of, it's OK to think about, but there's an easier way to think about this, which is I could decide that everyone's going to actually, V doesn't have to flip all these coins as they come in. It could just pre-flip one giant coin and decide what is the number of shocks it's going to take to kill me, right? I could just turn these P1, P2, and P3 into just an a priori decision, and I'll just consult that decision when I have to. And so the model in the previous slide is actually equivalent to the following thing, that each node V is going to just pick a threshold L of V at the very start of the process. That is the number of shocks that's going to kill it. Okay? So it's going to be effective. And now what we do is, this is now a very, very simple model to state. I take a graph. I, at every node, draw a threshold from this distribution mu of j. And mu of j is basically defined by sort of taking the prefix sums of these things. It's sort of direct translation. Okay? So mu is sort of the basic object here. You draw from that distribution, you get some numbers. And then you simply run this process. And I don't have a cool computer animation of this process running, but you can kind of work it out for yourself. Some nodes get labeled 0. 0 means you fail spontaneously. If there are no zeros in the graph, everybody's safe. OK, but there are some zeros. So there's a 0. That hits this person who has a threshold of 1. Now they get killed because they had a neighbor who had failed. Now these two neighbors have both failed. That kills this person in the third step. And this person never gets killed. They have a threshold of 4. And you can do the same with, in this one, these two zeros kill this guy, and this guy plus that guy kill that guy, and that's the end of the story. OK. Now, here's the funny thing. So this model, in a sense, is at the heart of almost anything you would like to make up involving contagion where there's some kind of non-uniform influence, right? Anything where earlier shocks weaken you, or even where earlier shocks strengthen you, it's going to have to somehow deal with this kind of a question. And so I view this as sort of the minimal element special case among many, many models. And so what kind of jumped out of this is this model, which I've now told you the whole model, is extremely hard to think about. It's very hard to analyze. And so it becomes kind of an obstacle, because we're going to need to understand this if we want to go on and understand any of these other models. And so actually, this is what I want to focus on. It turns out this model has some interesting behavior. So it's parameterized effectively by two things. One is the graph, and the other is mu. Right? And we're going to sort of look at this both ways. Sometimes we'll take mu as fixed, and we'll kind of look at different graphs. Sometimes we'll take graph as fixed, talk about different mu's. But this is the whole thing. So what's known here? So implicitly, sort of this goes back to work on the clique by Mark Granovetter in sociology, actually, who was in the Stony Brook sociology department when he did some of this, and Thomas Schelling in economics. And they thought, OK, we're on a clique. So a clique just means, everybody sees everybody, and so you find the zeros, and you count how many zeros there were, and that triggers some other people, and that's, and just a wave develops. And they sort of work this out by just drawing pictures and simulating what happened, or hand simulating what happened. Doing it on anything else, so even like trees or grids, I mean, grids are already quite complicated. Trees are a little easier. But even here, the techniques here are so different, and some of them are different levels of kind of closed form expressions. It wasn't even possible to compare cliques, trees, lattices. It was sort of one-off analyses for each of these, rather complicated. One special case that is sort of more handleable is diminishing thresholds, kind of the social contagion story where the probability of having a threshold of, and I guess I should actually put 0 there, that 0 exceeds 1 exceeds 2 and so forth. You're the most likely to get low thresholds. But we're sort of interested in the part where high thresholds are common. OK, so that's by way of background. So here's the question that we'd like to ask. The main question. We're going to fix a mu, right, a distribution over thresholds. And we're going to look over the space of all graphs, and we're going to say which ones are the safest, which ones are least susceptible to cascading failures. Now, if I just state the question that way, the answer is the graph with no edges is the least susceptible because nothing spreads. So we want to take the edge density out of consideration. So I'm going to look at all D regular graphs. So we'll call that the space script G sub D. Sometimes I'll be forgetful, and I'll really think the space of all connected D regular graphs, because if I have 2 identical copies of a graph, it behaves the same in both of them, and so it's kind of like I had one. So sort of all connected deregular graphs. Right, so what am I going to do? I'm going to look at some mu, and I'm going to look at all, so it's just a discrete distribution. Everyone draws thresholds some probability. And now I'll say the mu risk of the graph G, so it's parameterized by my 2 things, mu and G, maximum failure probability of any node in G when the thresholds are drawn from mu. Right? So it's a simple process. You draw a threshold, you run the process, and you see what is the chance that this node fails. And the question is, given mu, which graphs in this space, in the family of all graphs, deregular graphs, have the lowest mu risk, the lowest chance of failure? Right? In a sense, for a given mu defines a way in which failure is going to spread on this graph. Which ones are the most resilient? Right? The least susceptible to have shocks at them. This notion of the maximum failure probability is sort of one way to parameterize. I could also take a distinguished root node and say, I care about this root node. Now there's 3 parameters, the graph, the root node, and it's not very different. It's also not going to matter much in any of the kind of examples I work through, because those are all going to be vertex transitive graphs where they all have equal failure probability. But it'll be maximum. OK, now the reason I'm asking this question, as I'm saying, is because the answer turns out to be interesting and, in fact, to some extent, largely open. So the parts we can handle are already more complicated than we thought they'd be, and then there's a bunch we don't know. And so that's sort of why I call attention to this question, despite the fact that our intuition actually said this question was going to be easy. So when Bobby, Ava, David, Larry, and I sort of started thinking about this, the computer scientists in the group said, OK, let's dispose of this question, because we're like, we know what the answer will be. The answer is going to be the clique, right? Because every other graph is very big, and when you're big, you have there are many, many nodes, and they could all fail, and they could all come at you, and that's, and maybe it'll be non-trivial, but that's going to be the answer. And I should mention also that the space of all deregular graphs, I'm going to allow for infinite graphs, because the infinite deregular tree is actually an interesting graph in this family of questions. And it'd be sort of a pity to have to, if I had finite graphs, I have to do something weird, like sort of tying off the ends into a Peterson graph or something weird. So I'm just going to have an infinite tree, and that's allowed. OK, so which have lowest mu risk? OK, so this was our, I say, intuition from epidemiology, but it's the intuition shared by, I'd say, theoretical computer scientists, that the clique is very resilient, because you just have access to very, very few nodes, whereas you don't want to belong to a large connecting component.
What is a clique?
So a clique is a graph in which all nodes are neighbors. And so in particular, if I tell you it's a clique and I tell you it's deregular, I know it has exactly d plus 1 nodes. So, my pictures will all, with a few exceptions, have degree 3, so this is going to be my canonical picture of a clique. OK. David's intuition, the sort of thing he was hoping to model, actually, in this whole thing, was totally different intuition from financial markets, was that you want diversity of your neighbors because you want uncorrelated shocks, right? So this person is exposed to 3 sources of danger, but at least those 3 sources of danger are completely separate, as in conditional on what's happening to they're just independent things. And so, if you get weakened by shocks, then you really don't want to get a second shock. And so if they're all low probability events, then, what's the chance you're going to get hit separately from 2 of them? And so that was right? So his worry about cliques is that you get correlated shocks. OK, which we're like, OK, nice intuition. First of all, it's directly opposition to, the 2 intuitions are directly in opposition to each other. And we also thought, it all sounds fine, but we don't think that's actually going to happen. OK, so we began playing with some choices of mu. And let me just kind of get things warmed up by thinking about, different values of mu. So actually, you can already learn a lot, and I'll spend some of the talk just talking about the following set of possible distributions. It's just going to be supported on 3 values, 0, 1, and 2. So all thresholds are 0, 1, and 2, because you can get a lot of action to happen with 0, 1, and 2. there's going to be a very small s, a very small t, and then the remainder of the mass is on threshold 2. And actually, in the end, much of our analysis ends up looking at those kinds of distributions. I'm going to take some healthy threshold, h, and then I'm going to put very low probability on all the lower thresholds. So it's kind of like everybody started at h, and then something hit the whole system, and everybody kind of got these lower thresholds, and then stuff happened. Okay, so in particular, h here is 2, and we have these 2 small values. And let's think about s being small but fixed, and t being small, but I'm going to sort of slide it continuously between 2. Okay, well, actually, I might slide into a big thing. All right, so let's take the easiest possible threshold distribution, s 1 minus s 0. That means with probability s, you have a 0. With probability 1 minus s, you have a 1. Okay, how does that work? It says, look at your connected component in the graph. You've got some zeros, you've got some ones. If your component has a 0, that node fails. Everyone has a 1. It just spreads through the entire graph and kills everyone in that component. And if you're in a connected component that only had 1s, you survive. Okay, so that says that your failure probability, if you're in node R, is simply monotonically increasing in the size of the component you're in, because it's basically this question of, does one of the coins in that component come up heads and give you a threshold of 0. So therefore, the clique is uniquely optimal, because among all d-regular graphs, the fewest nodes you could possibly have in your connected component is d plus 1, and that's if you're a clique. Okay, good. But that doesn't really resolve this intuition, because clearly here you want to be in the small component. So we thought, all right, if this intuition is right about wanting uncorrelated shocks, it should happen at the other end here, where low probability of zeros, the rest is 2. Right? So now 2 is sort of a high threshold, and maybe that's where you start to see this effect. But that actually didn't happen either. So there's a slightly longer argument here, only slightly, that the clique is again optimal, in fact uniquely so, when the thresholds are either 0 or 2. And I did the argument by case analysis just because with a 4-node graph you could do that. Basically, here's the argument. What would it take in a clique for the root node to fail if all thresholds are 0 or 2? Well, if the root gets 0, it fails. If the root gets a 2, then in the clique, you need 2 zeros to trigger the whole thing. So basically, it's if and only if there are 2 zeros among its neighbors. But think about any d-regular graph. Right? So the condition for the clique is 2 zeros among your neighbors. Any d-regular graph, 2 zeros among your neighbors will kill you. And in any other graph, there are other events further away that also kill you. Right? So the clique is exactly that event. Everything else is that plus a union of some other positive probability events. And so the clique is uniquely optimal again. Okay, so this distribution, 0s and 1s, clique is optimal. This distribution, 0s and 2s, clique is optimal. And so here we were feeling pretty pleased with our intuition and ready to explain to David that if he wanted to see his intuition, we should extend the model and do something else. When we ran into the following surprise, and I won't prove this now, but I'll build up some techniques that let us prove it later in the talk. So there actually exists S and T. So I can, so these two are on a line segment between this one and that one, right? And so if I think from a sort of point of view of is this property convex, this is an average of those two. So I put some weight on 1, some weight on 2. I keep S the same as it was. And there exists a choice of T. Small, but larger. T is larger than S here. So the tree actually is safer than the clique. Okay? So in between these two extremes, there actually is a setting where exactly the thing that sort of seems safe about trees really is, and the thing that seems dangerous about cliques really is. Namely that you get these sort of chains of firecracker effects where in the clique, the 0 kills the 1, kills the 2, and that can't happen in trees. Okay, okay. So that's the that came as a surprise to us. And there's sort of a qualitative point here, which we hadn't expected from the model this simple. We were sort of prepared to start extending the model to start seeing this happening, but we didn't think it would already happen here. That extremely different graph structures one can be safer than the other, or vice versa, depending on the kind of contagion process you have. Right? Depending how you arrange the threshold, you would rather be in a kind of quarantined, safe, clustered thing, or maybe in a gigantic, expansive branching thing where your neighbors are diversified. Right? You would rather incur an infinite connected component than have correlated neighbors in some models. Okay, so good. So here's a question we can ask. So now that we realize the question is not to prove the clique is always optimal, what is the question? Well, so we thought, okay, so maybe this is the question. So G sub D, script G sub D is all d-regular graphs. Maybe it's all connected d-regular graphs. I'm going to be sloppy there. Gamma, oh, right, because for example, here's why, since much I'm being sloppy. When I say the clique is uniquely optimal, I mean a union of two disjoint cliques is equally good, but I sort of don't think that way. So all connected d-regular graphs. This is all distributions supported on these points. Let's say a set of graphs is sufficient if they're sort of on the lower envelope of this risk function. So that for any distribution, some graph in my family achieves the minimum mu risk over all graphs. So for example, I could say, okay, sometimes it's the clique, sometimes it's the tree, but that's it. They are a sufficient set. Okay? Maybe sometimes other graphs tie them, and certainly other graphs will tie them. For example, if I take the distribution that never assigns zeros, everybody's safe on any graph. Okay, so here's a second question. Do the clique and the tree form a two-element sufficient set for this threshold contagion model? Right? Is this it? Is it all about you should either be maximally clustered and avoid other nodes, or you should be maximally diversified and never have correlated shocks anywhere in the graph? And those are the two things, right? Okay. So for d equals 2, and the funny thing is d equals 2, we're talking about a very, very simple family of graphs. So what is a two-regular graph? So it's either a finite cycle or it's the infinite path. And that's all the graphs there are that are two-regular. But even here, actually, the subtlety I showed you before still happens. As in, sometimes the triangle is better, sometimes the infinite path is better. And indeed, when d equals 2, that's it. We can actually prove that they are a two-element sufficient set, and that's necessary, because neither is sufficient on its own, but together, one of them is optimal. OK. And in fact, uniquely optimal as long as you hand out zeros somewhere in the graph. OK. But it turns out, and again, so here, yet the next breakdown of our intuition, we thought this was going to be, the game was going to be to prove this for larger d. That was not true. They do not form a sufficient set when d is greater than 2. Yeah?
So actually, can I think of H as the Pareto optimal sort of set?
It's sort of the Pareto frontier of this, yeah. Yeah, I mean, I think of it as, if I picture like there's a dependent variable axis, which is the risk. And so now each graph defines sort of a surface overall. So mu is down here, and this graph defines some surface. And so I'm looking at the lower envelope of these surfaces. And these two surfaces, the clique and the tree, are the bottom, and everything else is somehow above them. Yeah. Yep, that's how you can think about it. Yeah. Any other questions about, because sometimes the sufficient set question is the crux of what we're thinking about. And in fact, it's going to turn out to be sort of the open question at the heart of this, which certainly I encourage people to think about, because I think it's just an extremely sort of clear, basic question about a model that I defined for you in the first 3 minutes of the talk. OK, so right, the surprise and what sort of turned this into really, I think, an interesting question is that when the degree is greater than 2, the tree and the clique are not it. They are not the whole thing. And in particular, I can invent a threshold distribution. It took some work to actually construct it, where, for example, the tree of triangles has lower mu risk than both the clique and the tree. So the tree of triangles is easier to draw than to describe in words, but you sort of know what it is. I take the complete three-area tree, and I replace each node with a triangle, and then I have them connect to nearby triangles representing other nodes. Okay. And actually, for larger d, I can create a generalized tree of triangles, where just I have d minus 2 edges going out to the other nodes. So I take it. OK. So I can actually get this to be a lower thing. So in fact, so the question I'm going to sort of build up to, and then I'll show you sort of our progress on it, is for d bigger than 2, is there a finite sufficient set of graphs, right? Is there a finite set of d regular graphs? I can say, this is it. These are all the possible safest configurations you can be in. Or is there actually sort of an infinite family where, as the distributions get sort of finer and finer, you sort of, yeah, push the structure out further? That we don't know the answer to. So here's some stuff we can say. So let me tell you a couple results, and then I'll start proving some stuff. That says, not only are the clique and the tree not a two-element sufficient set, there is no two-element sufficient set. And the way we're going to do that is, first, we're going to start with a generalization of the result that the tree can be better than the clique. In fact, what you can show is the tree can be better than any other d-regular graph. Okay? Not all at the same mu. Right? So we have to get the order of quantifiers here right. Namely, for every other graph, there is a mu, a distribution, where the tree beats it. Okay? So, all right. And in fact, you can say slightly more than that. For any finite list of d-regular graphs, there exists a threshold distribution where t simultaneously beats all of them.
Can I have a quick question? Maybe you guys are going to get
this.
So you've taken a very sort of worst-case scenario. Why couldn't you just say, if I had a distribution over the set of distributions, right? So it's uniform over that class. Say, what is the graph that's essentially where the largest mass would achieve?
I see. Yeah. So right. So the question is, why not just say the average badness over all distributions? Yeah. I guess right. So I guess the point is we're thinking about sort of assuming a distribution over the mu's is sort of not. Something that clashes with the motivation going in, which was that different domains are going to have different kinds of mu, right? So if I'm asking about disease versus social contagion versus financial contagion, very different kinds of mu's. And so asking sort of which graph is safest in some aggregate property, in some aggregate sense, you can, of course, have a distribution that's only over the kinds of mu's that you're interested in, but then that starts to get closer back to these questions. I should mention there's a different averaging question, which is if I'm talking about sort of the average failure probability of a node in the graph, to the extent I can take a well-defined average over the infinite tree, that goes through fine, and that would be roughly the same thing. There's another question, yeah.
Yeah, so a question about the motivation here, because every mu corresponds to a different system. You said like finance or...
well, I mean, all of them are toy models, but yeah.
So why would you expect, all such completely different systems to have something in common somehow? Like,
well, I mean, all of them are not clear, but I mean, certainly our intuition going in and the intuition we, I mean, it's one of these things where in retrospect, sure, it's fine that many complicated graphs all exhibit optimality, but certainly going in, we and the people we kind of, talked to build our intuition felt like, yes, there are different things. So, okay, it makes sense that the clique or the tree could be, but why exactly, say, the tree of triangles has some magical property that's better than both the clique and the tree simultaneously is, I would say, not obvious, right? I mean, sure, it is entirely plausible that different graphs are good for different mu's, but sort of how many different graphs and what's the space of possibilities is... and for example, it's entirely possible that these are the only three, in which case that would say something strong. It would say that overall mu's, it's one of these three.
No, but I mean, like, one graph corresponds to a financial institution, the other graph corresponds to people getting...
I mean...
So why are you putting them together?
There's nothing about it that way, right? There's one mu. I mean, so first of all, these graphs don't really correspond to anything because they're simply deregular graphs to me. But I'm not putting them all together in the sense that there's a single mu, and we're just asking how different graphs behave with respect to it. It's sort of how much richness, right? I mean, mu is defined on whatever, d+1 numbers, right? The space of all graphs is enormous, right? So I'm trying to sort of drive the space of graphs to all sorts of different optima by varying d+1 numbers. Seems awfully strong because the space of all deregular graphs is astronomically big. So yeah, it certainly would not have been obvious to me, but we could certainly happy to talk about it afterwards. Yeah.
Does that give a counting argument that there's a maximum number of, given that there's a certain number of functions that you can construct from?
Not really. I mean, so first of all, of course, there's a continuum. I mean, so we're on the simplex, right? So it's all vectors on d+1 numbers, they add up to 1. And so, in principle, that thing, and there are some interesting questions about sort of what is the space, so that simplex now is partitioned into here's the part where the clique's best, here's the part where the tree's best. There's nothing there. We actually talked about, is there some just general argument there based on compactness that says, that, okay, there has to be, but not clear. Yeah.
Essentially what I was trying to get at my question, which is the size of the space in which one is governed, in some sense, right? Well,
yeah.
Maybe the tree and the clique sort of overwhelms, and these are just very, very special.
Yeah, it seems not actually. I mean, so at first we thought we were looking at sort of weird esoteric things, but it seems like large parts are actually. Also, I should mention, we also thought, and the analysis will actually further suggest this, that, what we're talking about are very small distinctions. They're all roughly equally bad, and it's just sort of we're arguing over low-order terms. That's also not true. In fact, the gaps between, sometimes the clique beats the tree. Well, so certainly sometimes the clique beats the tree arbitrarily, because the clique has failure probably 1. But sometimes the tree beats the clique by a lot, by like a factor of d, which is about as bad as you can get. So in fact, we're talking about big swings of basic graphs. Yeah, so there isn't any, I mean, here's what you should envision that could be happening and why we don't know about finite sufficient sets. What could be happening is that for each mu, there's a better and better graph which looks like the tree out to depth k, and then starts wrapping around out at depth k. And then that finally gets beaten by a thing that looks like the tree out to depth k+1, and then starts wrapping around. Right? And it's entirely, and that will now form some limiting sequence which ends up at the tree, but each of them is optimal somewhere, right? And that's sort of what could be going on. And there isn't sort of any general principle that seems to rule that out. Yeah. Yeah, good question. So so this is sort of the crux of the question, right? So taking all of this together, this is why there's no two-element sufficient set. The clique clearly is in any sufficient set because it's uniquely optimal. It can't be the clique in the tree that's the two-element sufficient set because the tree of triangles beats them, and it can't be the clique in anything else because then the tree would beat both of them. Right? So that sort of says the space is at least 3. Good. Okay. So that's so what I want to talk about now is techniques for reasoning about this. Right. So the first part is just sort of laying out the space of questions as we understand it. Second part is I want to get into some of start by building up to wherever it was back here, it's way back here. But the fact that the tree can beat the clique, right? We have this intuition that's about correlated failures, but what does it actually look like? Because if we can sort of unravel what that looks like, we sort of have a technique that we can make use of. And so the basic idea is, so first of all, because I'm going to try to show, I'm going to start by constructing mu's where certain things beat certain other things, I'm allowed to look in any part of the space I want to look in if I'm going to try to construct something. And the place where I'm going to look is this one I mentioned, where everyone has a default healthy threshold h, and then I perturb it by giving, for all smaller thresholds, some very low probability. Okay? So now it's parameterized by x0, x1 up to xh minus 1, followed by the remaining masses on probability h. OK. Good. So that's the space of all distributions. And the question of, is there a finite sufficient set even just for those distributions, even for just small enough perturbations, even that's open. And seems to sort of contain the crux of the question. In some sense, if I'm not in this part of the space, cliques tend to win. Because if there's big constant failure probability on nodes, you want to be in the small component. And so somehow the interesting part happens where I would argue sort of also the interesting thing from the motivation, which is things are fundamentally healthy, but stuff gets damaged somewhere in the system, and we want to see what happens. OK. So, and the idea is what we're going to do is actually to compare things, because in the end, working out contagion probabilities is a hard thing. I mean, from a complexity theoretic point of view, it's sharp p complete, which is sort of somewhere above np complete, somewhere near p space. That's sort of at the crux of why we can't just say, well, why don't we just sort of write down some expression and compare them? Because what the expression you have to write down is some combinatorial thing involving counting over lots of subsets. And so in order to do that, we want to basically constrain the counting, try to sort of control that process, and count locally around the nodes being affected. Okay, so I'm going to look locally in the neighborhood of some node and try to expand its failure probability as a power series in these variables. And then look at sort of the low order terms and try to compare low order terms and see if I can construct a mu with that. That's sort of the rough strategy. So, OK, so we're going to sort of expand out the. So here's an example. And one thing about problems that are sharp p complete is that it's hard to even work out small examples by hand. So I picked a really small example, this graph. So here's the node I want to assess its failure probability. And S is the probability of threshold 0, T is the probability of threshold 1, and the rest of the mass is on threshold 2. And again, think of S and T as very small. OK, so what is the failure probability of this? Well, so the way to work this out is with this, with the inclusion-exclusion formula. So here actually is the sample space of outcomes, right? All possible labelings of the graph. And I've drawn circles where failure happens. So failure happens here because the root failed directly. Failure happens here because two zeros. Oh, sorry, a blank, my notation. I'll draw zeros and ones. But because 2 is the high probability outcome, I'm not going to draw it. And in the power series approach, that doesn't show up as a variable in the power series. That's all the remaining mass. Okay? So I'm going to draw only the zeros and ones. So this kills it because the root fails directly. Here it fails because these two zeros kill it. Here it fails because it got a 1, and that 0 was enough to kill the 1. Here because the other one. Right? OK. So how do I work out the probability? Well, I need to work out the area of all these ovals. And so this has area S. This has area S squared. This has area ST. This has area ST. These, of course, all have a three-way overlap because 0, 0, 1 is in their three-way intersection. So I need to account for that. So first I need to account for, OK, first of all, I need to account for this pairwise intersection, which I double counted. So I subtract an S cubed. Here I subtract for, well, I had each of these three there are three pairwise intersections, right? Each of the three pairs here all collide here, so I have to subtract 3 S squared T, which is the double counted mass there. But of course, the way inclusion-exclusion works is I subtracted it too many times, so I need to add it back in one more time for the three-way intersection. Right? And so that adds a final plus S squared T, and I get that formula. And that actually is the failure probability. Right? First of all, questions about that? Because that's sort of what we're going to have to do on an arbitrary graph. And of course, doing it on a 3-node path and having to do all this makes it sort of clear why this is not appetizing. So we're going to try to do it in a constrained way. Right? We're going to try to only look at a few terms and see if those few terms are already enough to compare different graphs. That's the idea. OK. So in fact, this already modulo, we're going to have to actually make this precise. And making precise has one more sort of tricky step in it. But modulo making it precise, you can already start to see why we're going to be able to have a distribution where trees actually beat cliques. Okay? Namely, what are the low order terms in the power series expansion for the tree's failure probability? Now, the tree has an infinite power series expansion because there's a whole bunch of positive probability stuff that could happen arbitrarily far down. So there are infinite set of terms here. But there are only some terms of degree 2. So first of all, the root could fail directly. Secondly, any two of its D neighbors could fail. That's D choose 2 S squared. Or any of its neighbors could get a 0 and it could get a 1. That's DST. And all other terms have degree at least 3. Right? Which is nice because if this is actually a well-defined power series, and the problem is it isn't for all graphs, so that's the danger. But if we sort of take the suspension of disbelief, which will turn out not to be true, that you have a well-defined power series here, which you do for the tree and the clique, then I can make S and T small enough that these will be small compared to what I'm looking at here. Now the clique, well, I still have the S. It could fail directly. I still have the D choose 2S squared. I still have the DST. That'll happen to the clique. But something else happens in the clique, which is D choose 2ST. That's the probability that one of its neighbors gets a 0 and another neighbor gets a 1. And then although it's healthy, it has a 2, it fails anyway. Right? And that's the term that's going to be the difference. Because if I can make S and T small enough that these terms all die away, this is left, and it's bigger than all that. Right? It's what makes it. It's what pushes it over the edge. You know, and so what's nice is this power series technique, if we can get it to work, actually sort of makes concrete the intuition from the beginning that, you know, cliques are nice because you don't have far away neighbors, but they're dangerous because this, you know, this failure can ricochet off that failure and kill you. Right? And this is exactly that trade-off. This is the ricochet effect, but this is a whole bunch of terms. And so we need to get these terms all driven down towards 0 so that that thing dominates. Okay? And that's what we're going to be trying to do. Okay. So first I'll go through some just language about how to write out this power series, and then I'll get to the point where, in fact, we need to do something extra because the power series isn't always well-defined. How to write out the power series, it's exactly what you saw in the Venn diagram here. I'm just going to sort of write down some stuff. So, and when I describe it, I'll focus on this 3-variable version, you know, 0, 1, 2, because it's just easier to talk about. But you can do it for D variables. So, OK, so we're thinking in terms of events that kill the root node. And so I'll call that an explanation of root failure, or an ERF. It's a partial labeling. I'm going to label the nodes that get the non-default threshold. Right? So I'm going to have a 0, 1 labeling, or in general, 0 up to h minus 1. I'm not going to put down the h's. So that's the sense in which is a partial labeling. I say where all the low thresholds go. That guarantees the root will fail no matter how I extend the labeling. Here I don't need to extend it at all because I filled in everything. But here, the root fails no matter how I extend the labeling, similarly here. Okay? So that's an explanation of root failure. It's a certificate that the root is going to fail. Now, a minimal explanation of root failure, which I'll call a MRF, a nice sort of cute, cuddly term for something which kills the root, is going to be an ERF for which no proper sublabeling is an explanation. So it's minimal, right? This is not a MRF, but these ones were. This was a minimal explanation for why the root failed. OK. And what we basically did in that Venn diagram was the following general recipe. We go over all of the explanations of root failure, all of them. In an infinite graph, that's a lot. And we look at all the ones that sign I zeros and J ones. And we look at every way of writing it as a union of k different MRFs. And then in the Venn diagram, that's going to be a k-way overlap. And so in inclusion-exclusion, that's going to contribute a term of -1 to the k plus 1 times the probability it happens, which is s to the I t to the j. OK? And so this is sort of a recipe for how to symbolically grind out the power series for root failure. You just enumerate over all the explanations of root failure. You see whether you can write it as a union of k MRFs for different values of k. And when you can, you throw this term into the power series. OK. So for example, in this one, this is the one we saw from before. There are 3 ways to write it as a union of 2 MRFs, because it's 0, 1, and 0, 1. It's 0, 1, and 0, 0. And it's 0, 1, and 0, 0. Right? So there are sort of 3 different MRFs embedded in here, each pair of which is fine. So I get all 3 of them contribute a negative. And then there's one way to write it as a union of 3, and that contributes a positive big. OK. So now this will all be great, except for a problem coming up on the next slide. You know, we've all definitely said, and now all we have to verify is that it's a well-defined power series with a positive radius of convergence. You know, and if it has a positive radius of convergence, I can actually do this and drive S and T down towards 0. And I've actually, but that's actually not true. So not only does this not necessarily have a positive radius of convergence, it doesn't actually even, it's not even something you can necessarily write down, right? Because I'm talking about power series. I'm saying the coefficient on the monomial, say s squared, is obtained by going over all the explanations of root failure and just keep a running counter and just keep adding up +1 every time you see one of them. And eventually that will give you the coefficient on s squared. And that's great, assuming the counter ever stops. But it doesn't have to. So take this trellis graph. It's a very simple 4-regular graph. And consider the coefficient on s squared. Well, there's an infinite collection of minimal explanations for root failure that involve labeling 2 nodes with 0. Basically, I move out to the right k steps for any k, and I make those 2 things a 0. Right? Or I move out, right? And so those 2 things are a 0. They kill the 2 to their left. They kill the 2 to their left. And like dominoes, it kills the root. So I can't even write down the coefficient on s squared there, because there is no power series here. And you know, that's no problem. It just says the failure probability of the root in, if you put anything on 0 is going to be 1. But it does say that the strategy is not going to work, because driving S towards 0 doesn't do anything. Driving S towards 0, it still has probability 1. When S is 0, it has probability 0, but that's not helping me. OK. And it's not just this. I mean, I could, you could say, oh, OK, maybe there's a structure theorem that says I should watch out for trellises. But of course, it's never that simple. The trellis could be hiding in some other thing. So way down here, it sweeps out this whole band, which then propagates arbitrarily high up something that looks like a tree and kills the root. Right? So there's no nice structure here as to when the power series is not well defined. OK. So what we're going to try doing is finding, because we still would like to work out this notion that there exists incomparable graphs here with respect to mu. What we need to do is find sufficient conditions for the power series to be well defined and have a positive radius of convergence. That's going to include the graphs we're interested in. The cliques of finite graphs. We're not worried about that graph. That's going to include the tree of triangles, and then we can actually compare them the way we want to compare them. And we actually prove this theorem, for example, about the tree can be better than any other graph for different values of mu. Okay. All right. So that's what we'd like to do. But for that, we're going to need sufficient conditions for convergence. So you can prove it for the tree as a one-off. You can just prove that the tree does have a positive radius convergence. But it'd be nice to say what's the sort of broader class of graphs that includes other things. So here's how we need to figure out what conditions do we need to impose on the graph, sort of graph theoretic, structural conditions, to guarantee this. And the rough thing we need to do is we need bounds on the number of partial labelings that label k nodes, right? The problem here was there was an infinite collection of MRFs that all labeled a bounded number of nodes, and that created this enormous pileup. What would be nice is if, first of all, if the number of partial labelings that label k nodes and create root failure, the number that only label k is somehow finite for every k. That at least says I can write down a coefficient here. And secondly, that it doesn't grow so fast as to swamp the x to the k power, right? So it should grow only singly exponentially, so that for small enough x, it will actually have an actual radius of convergence. Okay? So I'd like the number of labels that label k nodes to be finite, and I'd like it to grow singly exponentially. And that's going to need some kind of a graph theoretic argument, right? So pretend you're in the tree. If you're in the tree, then I'm saying your job is to put down some, say, zeros, or some zeros and ones, that will cause the root to fail. And I give you a budget of k, right? And if you think about it, you can't put those k things too far out, because they're going to start coming up, but they're going to start hitting other things that only have 2s under them, and you're going to lose momentum. Right? That's the intuition. Right? So if I try adorning this tree with a very small sprinkling of zeros, I'd better put them close in toward the root if I'm going to have it reach all the way up top. And if I put them far down, it's just not going to make it. Right? OK. That feels like, so that's at the heart of what we would need in order to actually be able to prove convergence for more general graphs. So here are two conditions where you can run that kind of an argument. I didn't actually formalize that argument, but I'll formalize it when I actually get to the more general class of graphs. Here are two sufficient conditions where arguments of that flavor, that you just can't put the stuff too far out or it runs out of steam, work. One is this very simple condition. If the healthy threshold is more than half the degree. Right, so remember, the healthy threshold is what everyone starts with. If that's more than half the degree, then in fact, everybody has a well-defined power series. And so it was no coincidence, for example, that here the problem came, it was a 4 regular graph, and the healthy threshold was 2, which is half of 4. That was sort of like the outer limit of where this is going to go wrong. Once you do better than that, and so in particular in 3 regular graphs, which as we see is already a very complicated family we don't understand, 3 regular graphs, if the healthy threshold is 2, everybody has a well-defined power series, because 2 is more than 1.5. OK. The other one, which we wanted because maybe sometimes you want to have a low, I mean, we also want to think about very low healthy thresholds on trees and other things. Here's a different structural characterization that seems to be useful for this argument. Suppose that for every node in G, each connected component of G minus V contains less than H neighbors of V. Okay, so that takes a while to digest, but it's what's happening in the tree, it's what's happening in the tree of triangles. It says H is the healthy threshold. The graph is very, very decomposable at nodes, right? Any node I take out breaks it into components. And the components have a thin enough attachment to V that I can't pack H failed nodes on any one side. Okay? So if failure is going to hit you, and if you have threshold H and failure is going to hit you, it's going to have to come from at least 2 directions, because there's a bottleneck here. Right? Okay? And that turns out to also be a useful sufficient condition. So I wanted to walk through one of these two arguments, just so you sort of see how they work. And it actually is sort of, what you want to do is formalize the idea of the process runs out of steam, right? That if I only label k things, then it's not going to make it. And here the steam is going to be almost sort of not just informal, but sort of become the metaphor in the proof. Let's define a kind of potential energy in the graph. So I put down the initial labeling. I'm going to define a potential energy. I'm going to then run the process of contagion. And potential energy is going to start going out of the system as the process runs. I'm going to quantify how much it goes down. And I'm going to say the potential energy is always non-negative. And so if it hits 0, the process is done. There's no more it can do. And so what I'll argue is that, if you don't put the nodes in the right place, it's going to run out of potential energy before it hits the root. So here's what my potential energy. My potential energy in this case. So this condition was the slightly more tricky condition to name. It's the easier one to make up potential energy. The potential energy here is simply the number of connected components of failed nodes. Okay? So I give you a budget of k nodes that you can put labels on. You do it. Some nodes fail immediately. And as an induced subgraph, there's some connected components of that failed set. Okay? That's going to be my potential. Now, the point is, every time a healthy node, a node of threshold h, fails under this labeling, well, it can't fail because the failure couldn't have all come from one direction. Because it has threshold of h, and each component attached to it has less than h neighbors attached to it. So if it's going to fail, there's going to have to be failure coming from this way and that way, which means you have to put labels here and there are failed nodes here and there. And so a component here and a component here, at the very least, got glued together. The number of components has dropped by 1. Okay? So every time a node of threshold h fails, the number of connected components has been reduced by 1. Now, the number of connected components started at most k, because the most you could do is maximally disperse them. And so at most, k nodes of threshold h can fail. Maybe k minus 1, I don't know. Right? Because every single time, you've reduced the number of components. I guess k minus 1. So in total, at most, 2k nodes can fail. The initial ones you labeled and the k others. Yeah?
Components of what?
So connected component means I take the graph.
I know what connected component
Yeah.
is. I'm saying this graph is connected.
Right. So
I'm saying when you take each
number of
section,
components.
you got the disconnected, but like,
So
can
it's
you find that energy more precisely?
yep. So number of components of failed nodes, which was shorthand for take the failed nodes, take the induced subgraph on the failed nodes. That's now a graph. Count those connected components. Yep. Yep. So yeah. So number of components of failed nodes, not in the whole graph. Whole graph's connected. Yeah. Other questions about the argument here? So most 2k nodes fail, and they form a connected set walking all the way back to the root, because they're an explanation for the root failure. So how many connected sets of 2k nodes can contain a given node in a deregular graph? Well, I can count that actually by basically depth first search. Namely, I describe the walk I'm going to do to reach all of them. And in order to describe that walk, I have to tell you which of my d choices I took at every step. So I could label each walk by this transcript of how I walked to touch all the nodes. And so there are d choices in each of order k steps. So the number of such sets is d to the order k. Right? So it's finite. And it's also singly exponential in k, which is what I need. Right? If s and t are less than x, the contribution of these terms is d to the order k times x to the k. And now by making x small enough compared to d, I can actually get that thing to converge to something as small as I want. Okay? Okay. And you can do this for the other one, right? The condition 2h greater than d. It's roughly the same kind of argument. I need a different potential energy. And the potential energy now is going to be the following thing. The number of edges going between failed nodes and non-failed nodes. Okay? So you put down a labeling of k nodes that failed. I'm going to look at the number of edges where one end has failed and one end hasn't failed. Okay? That's some number. And I want to argue that every time a node of threshold h fails under this labeling, that number shrinks. Why? Because this node, right, so h is bigger than d over 2. So in order to kill it, it has to have more failed neighbors than unfailed neighbors. So it becomes failed, so it joins the failed set. So these edges all leave by potential function. These edges all join, but there are fewer of these. It goes down. Now, this is a potential function that can actually grow, right? It shrinks here, but it grows when some unhealthy node fails, because now suddenly I might have extra edges coming out of it. And so it's a potential function that goes up and down. But of course, it can only go up when one of my unhealthy nodes fails. There are only k of those. It can only go up by d when that happens. And so I can bound the increase, because there are k nodes that can fail. Each of them can push the potential function up by a bounded amount. Meanwhile, these healthy nodes failing are all driving it down by at least 1. And so again, I get it bound on how many nodes of threshold h can fail. And the rest of the argument is the same as before. I run my depth first search argument. Okay? So essentially, graphs in which this process is sort of, has a well-defined power series are those, it seems, in which we can, the ones we found are those in which we can run this style of argument. That you try to get the graph to fail very parsimoniously by putting a few weak nodes very far away. But the problem is they can't coalesce to reach the root, and you can actually track that with this potential function. OK, so now that we have a way to write down this power series, there are a whole bunch of things we can sort of do immediately with this. One is I can actually go back to the tree versus clique and actually finally make it precise. Because now I actually have sort of some way to talk about those low-order terms in the power series. Second, I can similarly construct a distribution where I can prove the tree of triangles beats these two. And basically just need to figure out what the right values are and then work out what's now a much messier power series for the tree of triangles. But it all works out. And also this theorem that the tree beats any other connected d-regular graph. So roughly, here's how the argument goes using this power series machinery. So again, I want something that looks like, at the risk of backing up too far, I'm going to run an argument like this. Here's the tree. And now here's the other graph G, not the clique. And they might agree for a very long time, because this other graph might look like a tree out to very, very large depth. I just want to argue that the first time they differ is going to be the place where the tree is going to be able to win. So here's what we're going to do. Take this other graph that's not the tree. It has a root node. Well, because it's not the tree, well, actually, let's pick a node that lies in some cycle in this, right? There's going to be some cycle because it's not the tree. So take the shortest such cycle. It has length L. Now, the failure probability in G has an extra term, which doesn't show up in the tree, which is a single 0 can sort of follow both these paths up to the root and kill it. That can't happen in the tree. So there's an extra term. It's way far out in the power series. But you can actually show that it is the first time that these two power series differ. It is the minimum degree term on which they differ. And that requires a graph theoretic argument where you sort of look at, well, what could be different between them. And the sort of first time it happens would be this, because if they ever differed earlier, that would be a shorter cycle in the graph, essentially. Okay. And so now we just choose a parameterization where this becomes, so we set S equals T to the L, so that now we get a one-variable power series, and this is the lowest term where they differ. And so by driving everything else towards 0, the tree beats it. Okay. And again, as I said, it's these sort of arguments that should make you ask, are these differences you're talking about between graphs so small as to be sort of almost microscopic, or is there something deeper going on? And sure, if I have a graph that looks like a tree out to depth 100, then they can't differ that much. But if I have graphs that differ from trees close in, you can actually get huge factor differences, right? So the power series machinery is a way to show a difference and prove it. But in fact, sort of proofs that Bobby and I have worked out subsequently sort of get, for the special case of the tree versus the clique, show you can actually get wide separation between them. OK. So that's some of the concrete things you can do. I have the case of degree 2. Degree 2 is actually quite different. But let me actually wrap up with this. Then I'll just have a conclusion slide reminding you of the questions, and I'll take questions. So the case of degree 2, remember, first of all, it's totally different. So there's a lot on this slide. I'll walk you through it. It's sort of designed to be a compressed one-slide thing. Degree 2 is very different, particularly because the theorem turns out differently. It genuinely is true on degree 2 that the triangle and the infinite path are the only two optimal ones, right? So it's the theorem we wished we could have proved originally for the higher degrees and couldn't because it was false. But it's true here. So clearly we need some totally different thing. And we don't use a power series argument or anything else. We sort of analyze this combinatorially. Because two regular graphs, you can actually talk about all graphs, and you can just describe them all. Three regular graphs, of course, there's just no chance. OK, so here's how we're going to do it. We're going to compare the root failure probability f sub n on the n cycle to the root failure probability f sub infinity on the infinite path, t2. Now, we're agnostic on whether fn actually is smaller or bigger than f infinity, because that's going to depend on mu. Sometimes cycles are better. Sometimes the infinite path's better. What we want to argue is that there's sort of a tilt in these, if you think about f3, f4, f5, because f3 is the smallest one. The shortest thing you have is a 3 cycle. There's going to be a tilt in these so that if these all beat the path, then the 3 cycle beats them by the most. Right? So what we're going to say is either the 3 cycle wins, or if it doesn't win, then the path beats them all. So what we're going to do is use this principle that's sort of useful in a lot of analyses of these situations, where I'm going to assume everybody flipped the coins for their thresholds at the very beginning. But I'm going to only look at the coins when I have to. Right? This principle of deferred decisions that says when you're analyzing one of these complicated discrete processes, it doesn't actually matter when you look at the coin that got flipped. And if you don't have to look at it, don't look at it. Right? OK, so what's going to happen? So if the root has a label of 0, I expose the root. I look at it. It has a 0, it's over. It failed. And it failed both in the cycle and in the infinite path. Right? So I'm going to start out sort of just on the structure, which maybe I don't even know if it's a path or an infinite path or a cycle. I'm just going to start looking around the root. If it's a 0, it didn't matter what I was on, they all fail. If I see a 1 or a 2, I need to know what happens to the neighbors. So I'm going to start exposing things. And in some sense, a 1 is just a propagator. It says, I don't know what happened, go look to my left, right? Or go look to my right. So I follow runs of 1s until I get to a non-1. Now, a 1 here acts sort of like an OR. Namely, I follow the 1s until I hit things that are not 1s. And I have a 0 at either end, this fails. If I have a 2 here, I follow the 1s until I get to the end, and they have to both be 0. Now, if I get the answer to my question before I've exposed n nodes, then the outcome was the same on the infinite path and on the cycle. So the cycle, the n cycle, and the infinite path only differ on the part of the sample space where I'm forced to actually expose all of those things, what I'll call the wraparound event. Okay? All right. So now we can basically sort of wrap up by thinking about, OK, so what is the difference in these probabilities? So there are two events that are interesting. One is the probability of wraparound. The other is, on that part of the space, the probability of the path failing on wraparound, condition on wraparound, and the probability of the cycle failing, condition on wraparound. OK? So the behavior is identical without these. So the difference is simply the probability of wraparound times that difference. Now, it's clear that P sub n, the probability of wraparound, is going down with n. Right? Because in order to wrap around, I need to follow 1s all the way until I've hit n nodes. And if n is bigger, it's harder to keep generating 1s all the way as long as I need them. With a little more work, and I won't go into the details here, but happy to talk about later, you can also show that this difference is actually a decreasing function of n. Okay. So condition on wraparound, this difference, basically this failure probability is getting higher, and so this difference getting lower. And what that says is that I don't know whether this is a positive or a negative number. If it's a positive number for all n, if it's ever positive, it's a negative number for all n, then the infinite path wins. If it's ever positive, what that says, because they're both decreasing in n, is that the 3 cycles are going to beat them by the most. Okay. And so roughly what this shows is that the outcome happens at either of the extremes. Either the infinite path is best and it beats them all, or if not, it's on the shortest possible cycle. OK. So the case of d equals 2 is actually quite different. And we've thought about porting some ideas from this over to the case of higher degrees. Right? Because if you want to think about finite sufficient sets, it seems like one strategy would be to take a conjectural family, which would probably be a bunch of cliques glued together in a tree-like way. Right? If you wanted to conjecture, well, what's a finite collection of graphs that's going to... And to try to do this kind of argument, to try to start at the root and begin exposing stuff, and as long as it looks like one of these graphs, you're fine. And when it first stops looking like one of these graphs, to say something. But it, of course, gets much, much messier once you have degree higher than 2. OK. So let me just wrap up with sort of one final concluding slide, then I'm happy to take questions. So again, the sort of top-level point here is there are a lot of interesting models in the space of cascading failure. But somehow they all have threshold contagion buried at their heart. And it's a model that, again, you can describe in the first 3 minutes of a talk, but is very, very hard to analyze. And in part for fundamental reasons, namely that working out failure probabilities somehow inevitably involves the sharp p-hard computation of a gigantic Venn diagram and all the overlaps in it. OK. And sort of the upshot here is, d equals 2 behaves differently from d greater than 2. And I think, it's a very, certainly to us, very intriguing question. Is there a finite sufficient set for every graph degree, right? And it sort of is in the category of finite basis questions in graph theory, which often I think are sort of can be quite illuminating if one sort of is able to make some progress on it, right? Namely, is there a finite set of minimal obstacles to this combinatorial property? And I think it would already be very illuminating and possibly sort of the only possible tractable way to go about it is to think about this particular part of the space of distributions where I take a default threshold h and I perturb it downward. Okay. Lots of other stuff one could talk about. One could extend this model in any of a number of directions, right? I sort of went for the simplest one that was hard, but obviously heterogeneity in degrees, it need not be deregular. Heterogeneity in different nodes could have different threshold distributions, right? So you could begin trying to quantify, like, which are the linchpins in the graph because they either have a safer threshold distribution, and so they're going to be sort of a point of safety in the graph because they're a dangerous point in the graph. How does that relate to the node degrees? And then finally, there's a companion piece of work that the 5 of us, David, Larry, Ava, Bobby, and I did on looking at this kind of model, but from a strategic point of view. right? So this took the graph as given. I'm going to build a graph and see how robust it is. You could also sort of combine this with the literature in economic theory on strategic network formation, where I'm trying to form links strategically to other nodes to kind of maximize some payoff. And what was interesting in that literature is that it's always phrased as the question of, you know, I'm trying to maximize my social network within this organization, and so links are costly to create, but when I create them, they give me influence with other people, and so it costs to create links, but there's a payoff because now I'm connected to lots of people, and that's a great thing. Right? And that was sort of the sentence one of every paper in that literature was that motivation. And the funny thing was, when you go to think about strategic consequences here, it's the motivation is completely inverted. Links from you are great because you want to interact with people, right? So if I'm thinking about plugging into the world, say, you know, in terms of financial interaction, or I want to make loans to people that are going to give me some payoff, the links are great. I get value from each link I form. But the problem is the links connect me to this giant component where failure could happen, and if that failure happens, it's going to come and blow back and hit me. And so now links are good, but being part of a big component is bad. It's sort of the opposite of what we had before. And so we've looked at some of the game theoretic questions of how do you form those connections. And what's interesting there, and I'm happy to talk offline with anyone who sort of wants to hear more about this, what happens there is you get sort of the kind of thing you would expect in this kind of game theoretic situation, which is a tragedy of the commons develops, right? So in the same way that overgrazing hurts the shared meadow for the cows in the tragedy of the commons story, here the shared resource, the shared thing that's being overgrazed, is the basically safety margin between you and likely failure. Right? And the more links you form, the closer you bring yourself to that margin. And the problem is you aren't correctly weighing in the externalities you impose on everyone else. When you create these links, you also create a more contagious network, which is hurting everybody. And so everyone basically overgrazes the shared buffer between them and failure, and you end up with people creating too many links and pushing it right to the margin. So it's sort of the story you would expect, but of course, to actually work out that story in this context is quite complicated because we're talking about we only can handle it for the independent contagion model, but one's looking at sort of everybody's sort of poised right delicately at the phase transition between sort of the emergence of a giant component, which will be dangerous for everybody. Okay, so there's a whole strategic side of the story, which I think is also interesting. But in general, you know, I think what surprised us was, you know, we sort of poked this problem, we thought very gently, and outspilled a whole bunch of graph theoretic complexity that we found very intriguing. And again, I would sort of end with encouragement to any of you who sort of where this resonates with any techniques that you've thought about or have at your disposal to think about some of the questions here. Thanks very much. Any questions?
Me?
Sure.
So I don't know if this overlaps. So here's my question I'm wondering about. If I say I'm interested in infectious disease or something, and I give you a time series of people that come in contact with each other for either a brief amount of time, which would mean not very likely to transmit the disease, or someone's spouse and they're with each other all the time, and in the graph is set, and the time evolution of that graph is set. Can you then predict, you know, how many people will be infected, and how likely is this to be a disaster? How likely is this to be to not spread very far? Is that related at all to this?
It is related to that, and even for sort of independent contagion models, that is unfortunately also quite a hard problem. So the question of so if I'm on the complete graph, and so I say I have a room full of people like this, and there's some, sorry for the grisly image, there's some contagious disease here, right? So you know, each of us might come in contact with each other person here, but it's sort of in uniform probability. So that's a very, very extensively worked out, very elegant area. That's the theory of the emergence of the giant component in random graphs. The problem is the instant I make that not a clique, but make that an arbitrary graph, very, very hard to work out sort of what is the threshold at which a giant component emerges. So yeah, I mean, so this is sort of one approach into that, where we're looking at, you know, trying to deal with the family of all graphs, but looking at sort of constrained, you know, distributions, you know, and sort of answering what we can answer. But even if you want to think about sort of arbitrary graphs, and you want to think about even just uniform probabilities, it's a challenging problem. But it's a very natural question. I mean, it's also one that one can handle through simulation, for example, right? So it's one where you can sort of take the data you know, try to learn some model for the contagion process, and then just run simulations and see what the infection spread is. Yeah.
So the way in seeking restrictions is by means of considering particular kinds of graphs. But I was wondering if the way to reduce the complexity is to take a realistic element, for example, in social networks, that thresholds are correlated, and see if based on those restrictions, the problem becomes much more accessible or perhaps more complicated.
Right, interesting question. So you're saying like my threshold, so we're drawing thresholds, but my threshold is like your threshold.
Yes.
Yeah. Yeah, interesting question. And of course, right, then there's leakage between the threshold processing and the graph because I'm similar to my neighbors who are in the graph that I'm analyzing. Yes, my gut reaction is that gets more complicated because I can't do these counting arguments, which were the only leverage we had on it, go away because now I'm sort of counting over this complicated conditional probability. So, for example,
clustering the dangerous people in a particular area.
Possibly, yeah. Certainly for these techniques, right? I mean, so the fact that I blithely wrote down S to the I, T to the J meant I was independently choosing thresholds. And the instant that didn't happen, yeah. But yeah, with correlated thresholds and say, okay, the dangerous people are all in one place, I could see it getting more tractable if you said, for example, the dangerous people are all in one place in the graph. So they're all in one connected set, which says it's sort of like there's only one dangerous node. I could contract that into a single supernode, and now I'm looking at sort of failure radiating outward, and yeah, then you might get some leverage. If it was sort of arbitrary, I don't know. But yeah, it's a good question.
Yeah, let me, at the risk of embarrassing myself, throw out a conjecture answer to your sufficient set. So there's an operation that you did to go from the tree to your tree of triangle.
Oh yeah, the Y delta transform. Yep.
Yeah. So you just iterate that on the click and on the tree, and you get two infinite series. And that's it.
It's a good question. Now, right, so if I iterate that gives me, on the infinite tree, I get an infinite family of graphs going on. So that would be, I see. And so the argument would be that, so this would be a,
property from your
so but the claim would be then that there is no finite sufficient set. Is that'd be the conjecture, yeah. Possible.
He's proposing a specific way of proving it, I think.
A way of proving, as in a way of generating an infinite collection of minimal.
Sufficient. Yeah.
Well, so sufficient. The problem with sufficient is it could be a big sufficient set, then there could be a smaller sufficient set.
Yeah, I agree.
So, interesting question. That could be a sufficient set. I guess simply proving that's a sufficient set wouldn't, on its own, answer this question because now I've found an infinite sufficient set. But of course, the family of all graphs was an infinite sufficient set. So
it might be the smallest one.
Right. That would be
such control with your power series that you could show that you need every success series.
Interesting question. Right. So if I expand this out, certainly if you could show that every single one of these was optimal at some mu, then it would be a negative answer to that, which would be, yeah. Interesting. Yeah, that's entirely possible. I think about it. Yeah.
So you just mentioned that like financial systems are wired as cliques or like spin glasses, if you want, instead of trees, and that's basically maximizing the risk of failure, right? So what's the incentive there?
I mean, it's hard to say that there are cliques or there are trees. I mean, let's see, if I back up through, I mean, so the overnight loan network as collected by Fedwire, for example, was that thing, right? Which is not a clique or a tree or anything really comprehensible, right? I mean, so the actual overnight loan network is going to be something that clearly that doesn't nicely fit in any of these. It certainly has a core periphery structure, right? So there's some large institutions, and then there are a whole bunch of small institutions around the periphery, and there's a lot of edges going from the peripheral nodes into the core nodes. So I think if one wanted to say any kind of graph that's an abstraction, it should at least have, and I'm not going to propose a graph that has that, an exact family of graphs, but it should at the very least have a core periphery structure, where there's a core very high degree nodes, they link to each other, and then there's a whole bunch of very low degree nodes who don't link to each other but do link into the core. Right. And I think that, so say dense random graph in the middle, very unbalanced random bipartite graph next to it, right? So on the right here I have a near clique, and then with high degree nodes, and on the left I have a huge number of nodes, and I have a random graph where these guys have low degree and those guys have high degree, so the sums of degrees work out. If you want to sort of start from a toy model, that would at least have the kind of qualitative ingredients that we see when we look at this stuff. But yeah.
That sounds like a too big to fail system.
I mean, it's a system with a bunch of very high degree nodes in the middle, and yeah. I mean, I guess part of this, right? I mean, too big to fail is a fun phrase, of course. But I mean, part of this is to try to sort of move the question in the context of even these very simple models to the question of connectivity, not bigness, right? I mean, as in, you know, certain nodes here obviously play some role in transmitting failure or not transmitting failure. And, you know, I think that's probably in the end sort of part of the question. Any other?
Well, if there are no more questions, I'll say John.
All right. Thanks again.